Hello everyone. I want this to be a decent episode because we're going to do something different here for once. Instead of me just dumping you with hard science and maths and stuff like that, because the geophiles are supposed to be more technical episodes, but we're going to have fun with this one. What we're going to do is we're going to speculate about future plate motions and stuff, and then we'll go over some of the nuances of plate tectonics like I have in my other plate tectonic videos, all right, for you. So we're going to have fun. All right, and we are going to use this as well. Some of you may have seen this already. I showed it off to you when it came. This is a magnetic globe. I can actually stick pins on it for you. You know what I'm talking about, so I don't have to go like this all the time and stuff like that. And I even got a blow up 1 or 2 globes for you, so I can do dry erase on it for you. Granted, they are not exactly spherical, but they'll work for what I need to do. And as you can see, I don't wish blowing these up by hand on anyone. So you'll see some writing on this too and diagrams on this. The reason for this is twofold. First of all, sometimes my drawings aren't the most accurate of North America, and here I already have it, and that's what we're going to be talking about. And I definitely, number 2, do not want to mess this up. So, hence these cheap little $5 blow-up globes. I have already told you we're going to be talking about plate tectonics, but specifically plate tectonics and what if, as if certain things may or may not happen on Earth during plate tectonics in the future. In the upper right, you will see a date. That will be the date of recording, as this is probably going to take several days. Some of this stuff isn't going to be stuff you're taught in basic plate tectonics 101, if you will. But I will keep it simple. I will not get any math for you as promised. I will keep that at bay. One of the things I want to talk about first is Euler or Euler poles, depending on who you ask. I'm not going to be that picky about it. Well, what is that? Well, as you can see here on the globe, the Earth, I spin it and it rotates. I think that's the correct direction, counterclockwise, yeah. It rotates about an axis, all right? Just like that. So the entire planet rotates once about that axis in 24 hours. That axis is an Euler pole. It's just the whole planet moves with it. Plate Euler poles are different. They are axes of rotation, but they are not the entire body of the planet. They only involve the lithosphere. And as we know, the lithosphere and the crust together, and as we know, the lithosphere is divided into about a dozen major plates that move about the continents and the ocean crusts with them. That is one of the key differences as to why it's different than continental drift. Can I demonstrate this for you? Yeah, I can, and I'm going to on here. I'm not going to draw it because I got a nice 3-dimensional object here. What I'm going to do is I'm going to take just 3 pieces of paper, which are going to serve as our lithospheric plates. I am going to place them on this globe. Okay, you are going to have to use your imagination a little bit here. Pretend these are 3 plates on the Earth, these white pieces of paper. It doesn't matter what plates, it's for demonstration purposes. As you can see, I have put these 3 magnets here. Those are going to be our Euler poles, our axes of rotation of the plates. Now, plates do not propagate the entire planet. They exist as isolated blocks connected to other isolated blocks for all intensive purposes, but they move relative to each other around their Euler poles. And that's something we're going to have to look at later. When I actually do model it, you're going to see it's hard to do relative movements because all these things are moving relative to each other. So it gets a little confusing, but I'm going to try to clarify that for you. So if this plate is moving this way, and this one's moving this way because of spreading, and then this one's moving this way, eventually what happens, as you can see, relative to one another, the plates all move. All right, you see that? So they're going to do their thing, and this plate eventually becomes consumed, and this one moves over based on their axes of rotation or their Euler poles. And we can actually model this. We can actually take this kind of stuff into account. And if you guys see black and white drawings in this video, They're all from this book. This is a Tectonics textbook. It's from the 1990s, but it's still really good and really shows you the detailed workings of plate tectonics and how complex this whole thing really is. And yes, there are a lot of maths in there, but that's just so you know. So you saw me moving those plates about the globe on those three with the Euler poles, and you noticed one went under another one. Well, what exactly happens with that? Well, one just doesn't go over another one usually for an extended period of time. What eventually happens is you get a subduction zone, and there's basically 3 plate boundary types. So let's tackle those first, and many of you may be familiar with this. This is something they do teach when they talk about plate tectonics in general. You have convergent, and just like that suggests, it's where they come together. Divergent, where they spread apart. And transform, where they rub up against one another. We have some examples. These pins just highlight some of it. We have the Mid-Atlantic Ridge here. There's subduction going on this side of North America, and it's going to get a little more complex than this. And right here, this orange pin, we have a transform boundary, because not only do we have subduction here, we also have spreading, and this is going to come into play with our model later. This is going to get extremely complicated, at least from a predictive standpoint. So the Earth isn't getting any bigger. Plates don't exactly one doesn't just move over the other. Convergent ones, subduction, we'll tackle that first. Here we have our generic cross-section through the Earth representing convergent boundary, where we have subduction. This is just a generic cross-section. This is your continent. This is not to scale. None of these are going to be. This is your ocean plate. We have basically 2 types of crust. We have continental crust and ocean crust. That's the 2 basic divisions. This is more mafic and made of heavier minerals. This is more felsic, made of lighter minerals. In general, oversimplification, but let's just go with that. And here is an ocean, doesn't matter which one. Well, as these collide, what happens is this plate moves into the mantle. This is our mantle, and it is convecting a little bit. And I've done lectures on this before, so I'm not going to talk about that, but it's not a strong enough driving force to actually move the plates in and of itself. It's a part of the equation, it's not the whole equation. And the mantle is a solid, so you got this more solid, harder, more brittle crust being subducted into the more ductile underlying mantle. This is lithosphere, this is lithosphere. Continents are really just along for the ride. They're more buoyant. They don't really subduct. There are some special instances when we suspect it is possible, but those are talks for other times. So this is a convergent boundary. You have a plate being recycled and reincorporated into the mantle. We also have divergent or spreading boundaries. Once again, generic cross-section, not the scale. These are continents, and these are the ocean crust and lithosphere. I'm just combining the 2. Now, even though it looks like they're different here, that should connect, they're not separated. They do connect, and this is one plate, this is one plate. It's not, this is a plate, this is a plate, this is a plate, this is a plate. That's not how this works. Continents and ocean lithospheres move about together on a single plate if they're a part of that plate. They do not move independently until certain things happen. But in the spreading center, you have magma, you have the plates moving away from each other. What that does is that releases pressure in the mantle, causing melting and magma to rise and make a little seamount like the Mid-Atlantic Ridge, which I'm sure most of you have heard of. And this will continue until some things happen, because everything doesn't continue forever. All right, thus far we've covered Euler poles, and a quick note also on those is that Euler poles can change as plates move about and reposition themselves. Even though, like, this is the Pacific plate, there are different directions things are moving. So you got compression in one area, extension in another. compensation to keep this nice spherical shape. Plate tectonics is a bizarre way for a planet to lose its internal heat. It really is. So you have what's called microplates or subplates involved in this. But generally, for long periods of time, they are stable, at least in the order of about 50 to 100 million years or so. We talked about plate boundaries. I did not go into transform boundaries because that's literally just where one plate rubs up against another. They're most prevalent in rift areas, rifts. When you have rifting, which we'll touch on this later, but basically transform faults are more common along rift zones than subduction zones, although they do happen there as well. The mechanisms, there are three basic mechanisms that drive plate tectonics. Your three basic mechanisms that drive the plates are slab pull. Geologists have been aware of these mechanisms for a while now. Most people are taught the next one is the dominant one, but we are slowly learning, and the original concept came out in the 70s. Matter of fact, I think it's as old as I am. But it was quickly discarded in favor of this one. And this is what you see in all the textbooks, mantle convection, all just mantles churning. Remember, the mantle is a solid. Yes, it can behave like a fluid over long periods of time, but so can any rock, even the crust at the surface, but we don't consider it a liquid. It is a solid. It's just a ductile solid, as where the lithosphere is usually, not always, but usually a brittle solid, all right? So this is slab pull. Basically, what that is it's a gravity-driven system. When you got subduction, in your subduction, you got two plates, they meet, or one plate, or whatever. This is just a generic ocean plate, nothing special, just like the other cross sections I showed you. Here's an ocean for you. What will often happen is you get towards the center, you get an old, dense plate. It's thick. It doesn't want to be buoyant anymore, so it's going to fracture. And what's going to happen is that's going to initiate subduction. You can get subduction against an ocean continent, against a ocean plate as well. That doesn't have to just be ocean continent. So subduction will start via gravity and lack of buoyancy. And this pulls. What that does is that drives this. Your spreading centers that I showed you, where it's rifting apart, that force is not strong enough to push plates apart in and of it. It's actually the weakest. These are the order that we suspect them to be. This is the weakest. Those mantle plumes in the Mid-Atlantic Ridge and other ridges tend to be shallow relative to other things. Some are deeper. We'll talk about hot spots, just not right now. This is the one everyone sees in the textbooks and in YouTube and wherever, as they see this one. And mantle does convect. But when you do the maths, when you run the equations, plate velocities, especially in a plate as massive as the Pacific plate, which we're going to talk about, the subduction velocities are far greater than rift velocities elsewhere, than spreading velocities. Now, that variation shouldn't happen if the mantle is consistently convective and driving this whole thing. It would be the dominant force if we had more consistent velocities between subduction and rifting, and we don't. And velocity, I'm talking about plate velocities, I'm talking about centimeters per year, millimeters per year, whatever, something like that. Yes, I realize since they go around Euler poles, there's angular momentum that can be translated into, mathematically, velocity, linear velocity. I did that in an episode for you a while ago. That is a thing, all right? So these are your three major components, mechanisms that drive that. So let's talk about plates. The largest plate on Earth, surface area wise, doesn't have any continental crust on it at all. Continental crust holding cratons, let's say. And that is the Pacific plate. This is a rough outline. Pretend this is a sphere. And as you can see, this takes up a huge part of the planet. On here, the more spherical, well, you can see the boundaries really well. This is essentially your Pacific plate. It is huge. Hawaii's sits near the middle of it. And this thing has some complex motions. Subduction is occurring over here. Subduction and rifting is occurring over here. We'll get into that. It's important for our future development of North America as a continent. Now you can see, let's turn it this way. You can see this is the boundary. This trench outline here. You see this? See how much of the Earth curves there? This is not stable. The Earth does not like to have enormous plates. It is divided generally into large plates, but these huge plates are not stable over long periods. Okay, cross section of our Pacific plate, not the scale, not an exact match, but it'll work with the curve of the Earth. Okay, over here we have subduction with a neighboring plate, and over here we have spreading. You know, North America would be over here. This would be the Japanese islands over here. And what you can see is I've drawn the lithosphere kind of bumpy on the bottom, and that's what happens. There are areas that are anomalously thick within the Pacific plate. That's due to a combination of things. It's due to old dried out magma chambers that have solidified and attached themselves to the bottom. It's due to age. As the crust gets away from the spreading centers, the oceanic crust, it gets thicker. It gets less buoyant. I've already explained that. And so it thickens. So whatever causes this thickening, you see this here. This is why ridge push doesn't work. There's no way a mantle plume that's about right here is going to push this around the planet. It doesn't have the mass. It doesn't have the velocity to do any of that. Not to mention, in mantle convection too, you'll have your mantle convection. It might be like this right here and down here, but it could be like this over here too. But this doesn't really disrupt this, we don't think. And so you've got an upwelling here, but no rifting. And it depends on how big these cells actually are. We aren't very sure. There are some people that are proponents of whole mantle convection. There are others just shallow. I think it's a combination of both. But anyway, before I digress too far, what happens is eventually, just because this gets so thick, just like I showed you, it's going to break. All right? This is going to get so thick, it's going that slab pull, that gravity-driven system is going to kick in. And this is going to start subducting somewhere else and come down into the mantle here. This, as a side effect, if it's not being pushed to a rift elsewhere, is going to shut off, and it will stop and just become a dead subduction zone. This happens all the time for our modeling and stability, and due to plates being around Euler poles, spinning around those, this plate is just too big. It's just simple physics of the thing. So eventually, somewhere, this is going to happen. Now, although ridge push is not dominant, but now we're closer to where this spreading center is. And this is an analog to the East Pacific Rise, which I'm going to talk about, because the East Pacific Rise is on the west end of North America. And its plate velocities are far greater than the mid-Atlantic ridge plate velocities, even though the North American continent's overriding it. And I think that's going to play key into the development of North America. But anyway, so as this gets closer, this plate now breaks here. This is going to increase. This spreading is going to increase a little bit faster. Now, if that happens, you're basically locking the spreading center into place. A lot of times what happens when plates collide and a plate with a continent at the edge hits an oceanic plate and the oceanic plate goes under, that continent will just move across it until it hits a spreading center. And as it goes over a spreading center, it'll shut that spreading center off, kind of like the subduction zone was shut off. So that will happen. But I don't think that's going to happen with the East Pacific Rise or the west end of North America, especially if this occurs. And I think it's actually happening right now. The beginning stages are going, and this is where I think it'll break somewhere along this line, perhaps. I don't know for sure. Like I said, it's speculation. It'll increase that velocity of this plate as it pulls down. It might slow it first until this subduction gets established. Now, you might sit there and say, well, since it's a smaller plate now, isn't that going to decrease this because it doesn't have the mass behind it to pull that slab even harder? No. And the reason for that is because the Pacific plate is so big right now, you have to deal with the curve of the Earth. All right? The plate, the gravity exerted on this plate is not the same here as it is over here. You've got this massive plate, and you've got the whole thing basically. I know gravity doesn't act exactly to the center of the planet, but for all intents and purposes, that's what it does. You've got this area here wanting to pull down, and the plate is actually moving slower than it would be once this happens. Before I can get into the meat of this, the predictions that I've been wanting to show you since the beginning of this video, I'm going to talk about some things that are key to shaping North America in the future from a tectonic standpoint, because ultimately the shape of North America and every other continent is dependent on what the plates do. It's not dependent on anything we can do or stop or start or whatever. Here you see I've written 4 things. The Basin and Range province. This is an active area of extension and has been for several million years in the American Southwest. Now, it's a proto-rift, if you will. It's a series of grabens where the continent has extended and added actual width to the continent over the past several million years. Will it form a rift? Some people don't think it will. I think it's going to, based on these 2 things. Yellowstone, which we all know is a supervolcano, but it's not as deadly as everyone thinks it is. And don't worry, it's not going to pop in your lifetime or your children's or your grandchildren's, and probably your great-grandchildren's either. But it is significant because there is a plume under there. The East Pacific Rise, which I've already mentioned, it's that rift off the west end of North America that is spreading much faster than the Mid-Atlantic Ridge. And this, everyone knows about the San Andreas fault system and everything, and it's really just a complex transform fault, but I don't think it's that significant. I really don't think it is, because if you look at the big picture, it's a transform boundary. I've already explained to you what that is. And I think this is a temporary situation. I think that as North America tries to override the East Pacific Rise, it's going to shut this off. You're not going to see Baja California up by Alaska. I'm going to show you this here real quick. Okay? This is my magnetic globe. This is the continent of North America, essentially right here. You can see the continental shelf on it. It's the lighter blue area surrounding the continent. And essentially subduction, I didn't put pins here because I didn't have enough. And even if I did, I wouldn't have done it because it's crowded enough as it is. But subduction basically follows the west side of the continent anyway, and you can see it there. And so we have active subduction going on the west side of North America. Basically on the east side, this is what we call passive margin. There's stuff going on down here that is complex. But through here, for the most part, nothing's happening. It's just getting wider as the Mid-Atlantic Ridge spreads apart. But there's a lot of stuff going on here. You're seeing all these pins. You're like, Steve, what? The green right here is essentially the San Andreas fault and the rest of the transform fault that goes under Baja California. And as you can see, these 2 rifting areas, which are the orange pins here, this is not considered the East Pacific Rise. It was connected at one point, but this is rifting here. So we have rifting next to subduction. This plate is being consumed. The plate that is being consumed under North America and has been for millions and millions of years is practically gone. It's just this little kind of remnant of it. But this is the East Pacific Rise, and I ran out of orange pins, but we can pull those down now, and we can just keep bringing it down. It goes down. These are a little off. It goes down like this next to South America, and eventually the rift meets up with a rift separating Antarctica from South America. So you can see we have this massive rift here. And we have the Basin and Range, which is the edges are highlighted by these pink magnets, and the yellow is Yellowstone. You can see there's a lot going on basically from here to here that is going to directly affect what happens to North America, not only within the next 10 million years, but within the next 200 million years. So we got a lot to talk about yet still. I've already touched on this, and I've already told you the basics of it. It's an area of active extension where North America has extended over the past several million years and continues to do so. The million-dollar question is, will it rift? I think it will. There are active plumes under it right now. There are lava flows that we have visited, either real close to it or just inside of the Basin and Range, that have happened within 1,000 years, like Sunset Crater in Arizona. So it's not like the volcanism in this area is ancient. It's still happening. And if it's still happening, it can progress and get further and further and further, and eventually the rift can form, which will eventually form a spreading center. And I think it will form a spreading center, because as North America continues to move over and consume the remnants of that Fallon plate and goes over the East Pacific Rise, which I've already shown you is an area of active extension, and it's far faster, the velocities, than in the Mid-Atlantic Ridge, I don't think the continent is going to shut that off. Usually it does when it overrides that. But like I said, North America is not being moved over the East Pacific Rise fast enough, in my opinion. Normally it would. That wouldn't be enough to shut it off, just the fact that the East Pacific Rise velocities are faster than the Mid-Atlantic Ridge. What's going on there is something else. Yellowstone. Yellowstone is a continental hotspot and supervolcano, and based on past eruptions, yes, a lot of lava, mostly rhyolites and stuff, will be ejected, and they will cover the land surface and change it, but it's not like it's all going to go at once. It'll be a series of eruptions over a period of time. It's my personal opinion that this is going to basically serve as the center for what we call a triple junction. If this is map view, like you're looking down at the surface, you know, scale of one of these is 100, 200 miles, 500 kilometers, somewhere in there, in case you're curious about that. So what happens is when a rift forms anew, as magma rises and pops up through the crust, at about this point, it forms a triple junction. You can see it reflected in the shape of the continents as well. And the Mid-Atlantic Ridge goes like this because here's a triple junction, and there's failed arms of these. They're called the lockogens, and I'm going to talk about those here in a second. But here's one, here's one, here's one. You can see how they kind of form these angles. And I think Yellowstone is going to serve eventually as an apex for a new rift. Because even though the magma chamber is not overly active right now, it is active, but not overly active. It's going to become more active in the future, especially as I've already talked about, the Pacific plate readjusts itself, and that East Pacific Rise starts spreading even faster in the future. And eventually, as triple junction forms with Yellowstone here, one of these arms eventually becomes extinct. I don't know which one. I'm just going to pick that one for illustration purposes, and that's called the lockogen. And that just happens most of the time, or a lot of the time, or it could become like a transform fault many times. This arm, instead of going extinct, will start to form, transform fault that way. Once this gets going, it may connect with others, etc., etc., etc. So if Yellowstone is going to serve as the apex or the center of a triple junction, how do we know where the other two are going to form? Well, we kind of have one forming already in the form of the Basin and Range extension that is basically due south of it. I believe that will become an active arm and will remain active. And the other arm will branch off to the northwest and meet up with the part that is presently being consumed in Canada of what remains of that spreading center up there, which you'll see when I show you the pictures and the animation. And I believe the failed arm will point towards the inside of the continent. It makes sense. It's the thickest part. Might as well as fail where you have no chance, right? And what that'll do is basically cause everything west of this yellow peg line to rift away and move from North America. Well, we have rifting here. We'll have rifting here. One of these has to give. Since it'll reestablish the East Pacific rise as the dominant spreading center, this is going to not fail, but it's going to complete our Wilson cycle. What will eventually happen is a subduction zone will form here, and we may already be seeing the signs of that. There have been, in recorded history, earthquakes right off here on the passive margin, which shouldn't be tectonically active, that have been attributed to slumps falling off the continental shelf. I don't think that's the whole picture. I think we're starting to get earthquakes forming here as the ocean crust is starting to fracture next to the continental shelf. And eventually the mid-Atlantic ridge will continue spreading, but this is going to come this way a lot faster and will eventually override it. Another thing that will happen is Greenland. You see, well, Iceland, we know the mid-Atlantic ridge comes up here and it comes like this right now. But there does seem to be tectonic activity under Greenland right here in the north part and some magma chambers that could form a new rift or redirect the rift. I don't know. It depends on what happens here. I do believe that because we have active subduction here and here, this is the edge of our Pacific plate. We have this mess in here, which does constitute a lot of felsic and mafic crust. But I think that the new subduction zone that's going to break this plate up, because remember I said that's not very stable right there. It's too large of a plate. It's going to basically cut it into half or a third to a half, somewhere in there. And subduction will commence and become even faster. And as for North America, eventually it will come back over here. And this part, who knows where it'll end up. It may end up depending on which Euler pole, because remember, Euler pole is going to make it swing this way or this way. If the Euler pole for North America remains roughly where it is, there's actually several because there's compensation structures. It's not a perfect Euler pole. It's going to swing this way. And this, I don't know, depending on the rift, it could. My guess is Euler pole probably be up here somewhere, so it'll just kind of swing this way. But, you know, that's pure conjecture. I have no basis at all for knowing where these things will ultimately end up, but it's fun to speculate about those type of things. Okay, so now that you know the method of my madness, let's get into the meat of this. I want to show you the slides of how I think North America is going to evolve in the future. So let's get this started and then I'll wrap it up for you. Just Google Zealandia and, nah, don't do that.